the physical properties of haloalkane. Okay, so physical properties means what about the solubility, boiling point, melting point, how it looks like that. Okay, so first one in the physical property, they are colorless in nature. Second one, they impact color on exposure to light. And second one, they have a sweet color. So these are the physical means in appearance they are showing these properties. They are colorless and some of them are colored. Which one have colored? The volatile halogen compounds means these kind of properties we can identify from there. Means if you look at the compound, we can identify these properties, right? Now we are moving to the melting and boiling point. Halogen derivatives have higher boiling points due to greater polarity and strong intermolecular interaction, that is dipole-dipole and van der Waals, than the parent hydrocarbon. So we know that between boiling and melting means we are breaking the force between the individual molecule. So between the individual molecule, the interaction is called intermolecular interaction. They are dipole-dipole interaction, hydrogen bonding, right? Then one more is there, van der Waals interaction. So among them, hydrogen bonding is a strong interaction, but all the molecules are not forming hydrogen bonding. Dipole-dipole interaction is there, so all the molecules are not forming the same. Means dipole interaction is not present in all molecules. The molecule which have a polarity means the electronegativity difference between the atoms. They will also only form the intermolecular, that is dipole-dipole interaction with the next molecule. Then van der Waals interaction, that is present between all the molecules because it is not due to the permanent electronegativity. It is due to the movement of the electrons between the atoms. So as a result, we know that electrons are fluctuating between the atoms. So one atom is getting a negative charge, other is getting a positive charge. That's why they are negative and positive in means in a particular moment. So they will change their poles. Got it. So with the increase in the molecular mass, the intermolecular attraction increases. Thus, the higher members of alkyl halides are liquids and solids. So when the molar mass of the compound is increasing, when the number of carbon atom is increasing, their intermolecular attraction is increasing. That is when the number of electrons increasing, the van der Waals force will increase, because van der Waals force means it is due to the fluctuation of electron. When more electrons are there, the interaction will be more because that charge separation become more. Okay, so that is the important thing. Next one, the boiling point decreases with increase in the branching. Suppose when the branching is increasing, I'm writing one compound, that is propane. So between propane molecule, I'm taking two propane molecule. Otherwise, I will take a butane. Okay, so butane, I'm taking two adjacent butane molecule. So in between this butane molecule, we have, see, 4 connections are there between the molecules. Okay, so at the same time, here 4 carbon atoms are there. I'm taking 2 methyl propene, that is CH3, CH3, and this second carbon contains CH3, and other one CH3, CH3, CH3. So here we can see one is branch, right? So if you compare this one, these two molecules, the hydrogen means the intermolecular interaction per molecule is here only 3, here 4. So when the branching is increasing, means the connection points are missing. That's why the intermolecular interaction is missing. So the boiling point is decreasing. So when branching among the compound is increasing, their boiling point will decreases. Okay, but when the chain length is increasing, the number of connection points increases, means boiling and melting point will increases. Next one, if you compare the melting points of para isomers and ortho and meta isomers, between these orthochloro means see here 2 chlorine atoms are adjacent, right? Here 2 chlorine atoms are in opposite. So in this orthoisomer, between 2 orthoisomers, the interaction present is only it is there, means the intermolecular interaction is there, but here the difference is this para isomer is more fit to that of the crystal lattice because of this geometry. So they will have comparatively high interaction with the next molecule. So they will have comparatively high boiling point. Okay, this is not due to any other intermolecular, intramolecular, nothing. This is due to the geometry, that is the symmetrical structure, symmetric structure of these para isomer. That's why they are more fit to the crystal lattice. So it is not easy to break the interaction between the adjacent para isomers than that of ortho and meta. That's why they have comparatively, the para isomers have a comparatively larger melting and boiling point because they are fit to the crystal lattice because of their symmetrical structure. Next one, density. The density of the compound, we know density D is equal to mass by volume. When mass is increasing, density will increases, right? So when the compound, when the mass of the atomic mass of the halogen atom is increasing, so because fluorine, chlorine, bromine, iodine. So iodine have a comparatively high molecular mass. So same number of carbon atoms are there. Suppose two carbon atoms are there, and halogen atom in one compound it is iodine, and another one two carbon atom with chlorine, another one two carbon atom with bromine. So which one will have high density? Obviously the compound containing iodine, because with the mass of carbon is same, but here the mass of iodine is higher than that of bromine and chlorine. When the mass is increasing, density is increasing. Okay, that is the thing related to the density of the compound. Now solubility. So haloalkanes are sparingly soluble in water. So a large amount of energy is required to break the hydrogen bonds of water molecules. So the solubility of haloalkane is lower in water. That is the reason. So haloalkanes are because in water, between the water molecule, the interaction is hydrogen bonding. Okay, the hydrogen bonding means intermolecular hydrogen bonding is there. But when the haloalkane is adding to water, the haloalkanes are not able to form hydrogen bonding with water. So when you add some solute into solvent, the solute solvent interaction should be stronger than solvent solvent interaction. Then only that solute will be more soluble in that solvent. But if you consider the solute in the solvent, the solute solvent interaction, that is the interaction between the haloalkane and water, is less than that of the interaction between water molecules. That's why they are not soluble. If the interaction between haloalkane and water is high, very strong, they will be highly soluble in water. So the interaction between here the solute is haloalkane. So in order to make a particular substance more soluble in water, the one and only one thing is the solute will be more, means the solute solvent interaction will be more than that of the solvent solvent interaction. Okay, that is the thing related to the solubility.